good morning. My name is Matthew Gopert. Let me take a minute to do a short introduction for myself. I've been working with Coastal Flow for a little over a year now, almost a year and a half, started last July. I work pretty closely with Tony, Gary, Brooke, and the audit department / gas accounting department. I work on many different types of projects, from monthly meter production to special audits. So I'm doing a wide range of work, learning a lot, and having lots of fun. And today I'm here just to give you all a brief presentation on an introduction to the fundamentals of orifice measurement. Now, the reason I kind of want to talk to you guys about this is, at Coastal Flow we process about 30,000 meters monthly, produce statements, send them out to the customers, and over 95% of those meters are orifice meters. So, it's by far the most prevalent primary element we see. So we kind of just want to give you guys a short idea, a quick understanding of how it works and why it is so prevalent. This is just a simple mock-up of a orifice meter. You've got your meter tube and you've got your plates in the middle. Now, the whole idea of measuring the flow this way comes from Bernoulli's principle. And simply enough, Bernoulli's principle kind of just tells us that when you see an increase in a flowing system, when you see an increase in the fluid velocity, simultaneously you're going to see a decrease in pressure. And so that's the whole principle of this meter. So what the orifice plate allows us to do is you take a shorter diameter and you force all the gas to squeeze itself through that diameter, and this increases the velocity. An easy way to think about this is if you all watered your lawn, played with hoses when you were young, you know how when you put your finger over the hose, it comes out and it sprays out and it comes out a little bit faster, it goes a little bit farther. This is the same thing happening here. You're shrinking the area for the gas, that the gas has to flow, so there's an increase of velocity. Now, as I was saying, this increase of velocity is simultaneously accompanied by a decrease in pressure, and this is kind of how we measure the velocity. We calculate the velocity. We measure this pressure before the orifice plate. We measure the pressure after the orifice plate. We know that there's going to be a decrease in pressure, so we see that there's a differential pressure over the orifice plate. And this differential pressure is proportional to the square of your gas flow rate. And accompanied by a couple other knowns, you're able to calculate your volume for a given period. So simply enough, you really need three main things to calculate your volume. You need your velocity of the orifice plate, you need the area of your orifice plate, of the bore of the hole in the orifice, or the orifice itself, and you need the flow time for your period you want to calculate the volume for. Now there's a couple other things involved, corrections for heat capacity, the changing of sizes, just like basically the metals will change with temperature, gas will expand and shrink with temperature changes, so there's a few other things you have to account for, but these are really the three main portions for calculating your volume. You use your velocity. Like I said before, you're going to measure your differential pressure and your static pressure. You're also going to have your temperature. Like I was just saying, gas can expand or shrink with temperature change. And then you're going to want to know your density based off the gas composition. You're going to want to know your density because heavier fluids are going to have a different effect, a different velocity through the same orifice. Lighter fluids are going to than lighter fluids. Just a kind of a quick explanation of how we get the volume. I have just our units down here. We have our velocity, a distance over time. This example was feet per second. We have our area of our orifice, feet squared. Multiply those together, you have your feet cubed over a time, in this case seconds, so that's a flow rate. You've got a cubic foot of volume moving over a certain distance in a certain amount of time. You multiply that by your flow time over your given period, which is seconds. You get rid of your seconds, you're left with your cubic feet of volume over that period. There's one final step. Gas is sold based off its energy, the amount of fuel, basically its fuel value that it can, basically the energy stored in its given volume. We basically arrive at this by taking the volume and having a heating value, which we calculate again based off our gas composition, and we arrive at the total energy of the volume. One thing to note is that liquid recoveries, liquids, you're going to sometimes have systems that are gas and liquids are not sold based off their heating value. They're sold based off their volume, based on component. So you're going to have your propanes, butanes, hexanes, they all cost different amounts of money. And so they're going to be sold based off volumes. Now, as I was saying before, there are several primary element types, even though ORF is the most prevalent. Quickly, that's a Coriolis on the far left. Up top in the middle is a turbine meter. This is ultrasonic down the bottom. It's got the electric nodes you can see here that pass sound waves, basically bounce off one pipe, one side of the wall, it comes back, and you got your positive displacement meter. Now, kind of thing I want y'all to take from this is, why